Today we'll be starting to talk about another really important mechanistic kind of pathway that organic reactions commonly follow. One of the things you'll notice about this is it combines some of the steps of the other various things that we've been talking about, like for instance the arrow push from the electrophilic addition to alkenes and alkynes, and also a little bit of that elimination type reaction like the E1s and the E2s. So without further ado, let's get right into it. Well, first of all, we're talking about EAS, right? I should mention that there's also an NAS, right? Nucleophilic aromatic substitution, which really is not as common as you're kind of led to believe. The ACS test does have a lot of questions about NAS, so we're actually going to spend a lot more time on that than I normally would. Electrophilic aromatic substitution is kind of the big one in town. So we need an aromatic system, so we're just going to choose benzene. And keep in mind, when I draw an aromatic thing, I could draw these like alternating double bonds just about any way I wanted. So this is actually going to be resonant equivalent to me putting the double bonds where you see the single bonds. So that sometimes helps in terms of doing one of these mechanisms, knowing that you can kind of just move those bonds around at your convenience. So what we're going to be doing, and we'll be going through a couple of specific note card reactions, but I wanted to show you the general steps of an electrophilic aromatic substitution, and I'll just show it with just kind of a general electrophile there. Very first step that's going to happen, we'll go to red because that's kind of what seems to show up the best for these mechanism type questions. And it really is going to look just like the electrophilic addition beginning, right? That idea that we're going to have this double bond swing out and attack our electrophile, initially ending up with a resonance form that looks like that. One of the things that you'll notice is I've highlighted the H that was there. So that's kind of a common step that I think will make doing these mechanisms a little bit easier. Is if you put any kind of carbon with a positive charge, if you show the H's that are right next to that, sometimes it helps to lead you to some mechanistic outcomes that you wouldn't discover otherwise. So one important thing is that in aromatic chemistry, it's going to be very important that we're very good at drawing resonance forms. So I'm going to explicitly show all the resonance forms, even though I really could get to the answer without doing this. Or I should say I could complete the mechanism without actually doing this. But it turns out that these kinds of arrow pushes are so important that I'm going to really explicitly, especially at the beginning here, when we see a mechanism like this, I'm really going to try hard to show all the different resonance forms. Okay, so there you can see the full resonance picture of this thing. Keep in mind what this actually means is that you have this like delocalized system that's all along this system of 5 carbons right here. And it turns out the final step of this mechanism I could show from any single one of these resonance forms, but just because this is the one that doesn't have any red arrows on it yet, I'm going to show it from the last form. You should feel comfortable with showing this step and getting to the product that I show with any of these different resonance forms. But the next step is going to be some sort of general, let's just put like another nucleophile in there. You'll see what these things specifically are when we get to the note card reaction section. But some nucleophile is going to come in, and much like we've seen with that E1 mechanism, a nucleophile will reach in, rip off an H, and reestablish our double bond there. And in this case, I've reestablished aromaticity. So the net sequence of steps here, you really notice that we've got kind of an electrophilic addition followed by an elimination, right? And so the net result of that overall is a substitution, right? So quite literally, we took this H and put an electrophile on there where the H used to be. So there is like a qualitative test for whether or not say you have a double bond or you have some sort of aromatic system that'll actually look for different byproducts. So here, the result of something like that, you'll notice that net what we've done is we've ripped off an H, right? And so That kind of, those sets of arrows right there are going to be things that we start to become really, really comfortable with. So let's take a look at some really specific examples. And just like is often true, it's really helpful to be able to put halogens on these rings, just for some of the same reasons that it was useful to put halogens on non-aromatic systems. We will have to talk about a whole host of kind of new reactions because aromatic rings don't react in that normal SN2 sense. But we'll get there eventually. The one thing that's important of all of your different electrophilic aromatic substitutions is that I always think that there has to be some sort of pot sweetening step, I call it, right? And the reason for that is keep in mind that an aromatic system, as we talked about, is incredibly stable, right? And sometimes it's really hard to, get these reactions to occur. So even though we talked about halogenations before, right? If we imagine this thing was just like a plain old double bond, this thing would do a kind of a double chlorine addition. It turns out because it's an aromatic substitution, we're going to overall substitute just a single chlorine. I'll show you how that happens in just a second. But we have to put some sort of catalyst in here, right? And the catalysts are going to start to play a really important role in a lot of these things. And it is often because of this, what I call pot sweetening step, which I'll kind of highlight as we go through different note card reactions here. So what I'm going to do in this case is I'm going to use a Lewis acid catalyst, in this case, iron 3 chloride. And we're going to go through the mechanism in just a sec, but what we're going to ultimately see at the end of this thing is that we put a chlorine on as a result of this, and of course we've got that HCl byproduct, and we'll regenerate the catalyst throughout the process here. So, as I said, first thing we need is a pot sweetening step, and these things generally don't involve the starting material to start off with. What we're going to do is we're going to put a chlorine with all of its, or elemental chlorine I should say, with all of its electron pairs, and we're going to draw out iron chloride in its Lewis structure covalent form here, and we are simply going to take this chlorine and we're going to attach it to an iron, which will ultimately lead to, or I shouldn't say ultimately, initially lead to this totally crazy looking structure here that looks like this, an iron with an overall negative formal charge. And so what we're going to do at this point, now that we've kind of sweetened the pot, right, really what we've done, oops, let's put in those other electron pairs. Really what we've done is we've really weakened this chlorine-chlorine bond enough now that just a hint of this reactive species being around is going to cause one of these double bonds to swing out. So let's just do it this way. And we end up with our initial intermediate. And as I said, there's going to be a couple of resonance forms here, so I'm just going to draw them without arrows because you seem to be pretty good at this point at resonance forms. Okay, there are my complete set of resonance forms. Hopefully I didn't make any mistakes there. And so the final step of this, we're going to have to show the regeneration of the catalyst, right? So that idea of a catalyst participating in the reaction but not being consumed, right, is going to be important. Oh, and by the way, oftentimes you'll just see something written like that, which is catalyst, obviously. Usually when you see catalyst, that's kind of a shorthand for saying very little bit of this is required, right? Just a rat's fart of it's like sprinkled into the reaction, basically. And so let's use a kind of a different resonance form to show the final step here. Just for variety, we are going to show that, and we are going to have one of these bonds swing out, and let's actually show it such that, and so we can see that as a result of the entire mechanism, right, we end up with that byproduct consistent with a substitution, right, the HCl forms right in this step. We've regenerated after this step our catalyst so that it can then participate in another reaction, and we've successfully put a halogen onto an aromatic system. By the way, I could have done bromine, in which case I could have done like iron 3 bromide, iodine, fluoride, things like that are a little bit more complicated. Fluoride would probably require like ammonium fluoride or something like that as a catalyst. Don't worry about that too much. Pretty much you can just think about these halogenations as basically the dihalogen and then the iron paired with whatever X3 happens to be. So let's take another couple of looks at some note card reactions. Another really important note card reaction, which I'll show you some of those generalities involving like a pot sweetening step followed by that addition and then all the resonance forms followed by an elimination, right? I'll just do that for you once more, and then I'll give you one other kind of pretty helpful reaction for us to know as a note card that you can figure out that you can probably figure out the mechanism for. As we go through this topic, I'm going to just kind of start with these basic 3 reactions that I'm throwing at you. We're going to talk about something else in the next couple of video lectures, and then we'll return to talking about some important electrophilic aromatic substitution, like note card reactions. Okay, so pot sweetening step. Well, the first thing we need to remember is how to draw nitric acid. So now we've got nitric acid, and we're going to actually have that really concentrated H2SO4 act as an acid now. That's a pretty unusual reaction, and that's why we needed such a high concentration of a really strong acid. Turns out the very next thing that happens, I'll just draw H2SO4 like this, is that we actually protonate this oxygen. And the species we at least initially end up with is our protonated nitric acid. And the second that this forms, it very quickly degrades into NO2 gas, which I think is called the nitroso. I can't remember. But anyway, we have as a reactive species this very, very electrophilic intermediate right here that is then going to undergo the reaction we've seen a few times. Looks a little bit like a scrunched mess, but you can see that consistent 3 resonance forms. You can see the full detail of what NO2 actually looks like. Oops, I should include my positive formal charge on there. And your final step is I'm going to have water come back in, reach in, do our elimination step, and we'll reestablish aromaticity. Okay? So, really helpful for a reaction, which we'll see why it's so helpful. Putting a nitro group on here. I should mention that this is one of the reactions in your lab. It's not quite benzene that we start with. It's also a really great way to make TNT, the explosive, trinitrotoluene. So we'll just learn one more reaction that's kind of helpful, and I'll leave you to figure out the mechanism. I forgot to say, this is a nitration. Won't talk about a mechanism here, but here's a really helpful reaction, especially for synthetic reasons, right? Because you'll notice that what we have here is kind of the beginnings of that tosylate type compound. And we can actually turn any benzene into a sulfonate with fuming H2SO4. All that fuming H2SO4 does, which may help you with your mechanism a little bit, is the reason it's fuming is that there's a gas in there, SO3. So try to figure out the mechanism for this. Remember your pot sweetening step and all those other steps that we talked about. Soon we will be talking about what happens when we're not starting with just a simple benzene, but instead have some sort of substituent on there.